Okay, today we will look at the common questions for some of the common questions for sound, chapter 13 on the textbook. Okay, the question that I'm looking at for today will actually be how to draw your displacement distance graph, your pressure distance graph. Okay, for sound, right, there's three graphs that we are particularly interested in. So for the first one will be your displacement distance graph. Okay, displacement distance graph is actually the graph of the shape of the wave itself. Okay, so how do we do it? Okay, here how we go. So let's say this is the original time. Okay, time zero. Okay, 1 second later, the waves are disturbed. Okay, and the arrangement is what is stated in in B. Sorry. Okay, so from this picture here, what you need to interpret is the motion of the particle itself. For sound, right, the convention that we adopt is that we will take right as positive, left as negative. Okay, so this is the convention that we adopt. What do we mean by that? Is that we take a look here. Okay, if we look at the first ball here, the first particle here, okay, so A, what does A mean? That the particle is actually at this rest position. Now, 1 second later, the same particle is actually at these new locations. And what can we say about this is that the particle has actually shifted to the right at a certain location. Similarly, if you look at the second particle, originally is at the original location. So now it has actually shifted right at a certain location, certain number. Okay, so how do we translate this information to a displacement distance graph is this? Okay, so let's take a look. So imagine this is the displacement distance graph. Okay, so this is the axis that we're looking at. Okay. Okay, a bit slanted, but it's okay. So now what do we do is this. Now, for first particle here, okay, for this first particle, this is the axis here is the equilibrium position. So now we are saying that at one time equal to 1 second here. So now we're going to draw time equal to 1 second. Okay, the particle has been disturbed, or the particle has been disturbed. Okay, so the particle 1, okay, the current position now is right side. I would say like maybe 0.15 0.15 cm. So let's do assumption. Let's say it's 0.15 cm is to the right. So right means plus, it means positive. So I will say that the first particle here, which is here, okay, I will say the first particle, yeah, give me a minute. Okay, let me call the line first. Okay, the first particle, oopsie, it's a bit slanted, but okay, we just make do with it. Okay, so I'll say the first particle, okay, is at 1.15 cm positive, means it's to the right. So it's, let's say 0.15. Let's say I'll take it as here. Okay, so this is 0.15. Okay, so what happened to particle 2? Particle 2, okay, is maybe 0.1. Okay, 0.1 cm to the right. To the right means positive. So 0.1 cm will be here. Okay, to the right. Okay, 0.1 cm to the right, which is positive. And similarly, if you look at the third particle here, originally at time 0, this particle is here. Now this particle is right side, let's say a bit of a distance, let's say 0.05. Okay, so it will be somewhere here, the third particle. And you take a look on this information, you'll find that the fourth particle is actually almost at the same position. I would say the rest position, the equilibrium position. So which means its displacement at 0, 1 second later will be actually 0 at the equilibrium. It's not disturbed at all. So if you continue with this plotting, let's say example for this particle, it'll be to the left, which means it is negative. So you actually have a graph, let's say you will have a graph that looks like a cosine curve if you plot it nicely. Okay, and this is how you get the displacement distance of the graph himself, of the wave itself. This is based on the position, okay, of the particles. And how do we decipher this graph? Is we look at individual particles at individual locations. Okay, so you literally have to see whether the particle has it moved to the right or has it moved to the left. Okay, then after you plot respectively. Okay, so for displacement distance graph, right, these are the stuff that you have to be careful. Okay, look at the dots and analyze it whether it's left or right. If it's right, by convention, it's positive. Left is negative. The other information that you have to do is what you need to take note is when we translate displacement distance graph to pressure distance graph. Okay, for pressure distance graph, you have to take note is that the convention that we use here is that for pressure distance graph, the convention that we have is when particle is at maximum amplitude, when it's being displaced maximum, okay, at the maximum displacement, the pressure it encounter is actually the least pressure, what we call zero pressure. Okay, but on the other hand, the object with the least displacement, I would say zero amplitude, zero motion, the pressure will be the maximum. And the third one that you have to remember is by convention, we take compressions, okay, as positive pressure, refraction as negative pressure. Okay, so first thing students always look at is how do I see whether the object is compressed or refract. Okay, here you have to look at the whole wave as a whole. If you look at time zero, right, you look at the whole wave motion himself, you'll find that the whole wave motion, there is a particular pattern, which means you take a look at these dots, which is not moving. You take a this dot, which is not moving. You find that for the first dot here, A, you'll find that the dots are actually squeezing towards this particular point here, which is, I would say, the particle on the left is actually moving to the right. The particle on the right is moving to the left. So there is this squashing effect at point A. If you look at point B, you find that the particles are actually moving away. For example, the particle on the left is actually moving left, particle on the right is actually moving right. So it's like it's being squeezed. It's being stretched out. So because of this motion, I will be able to see that particle A is actually what we call the center of compression. Particle B is what we call the center of refraction. Okay, and same thing what we are looking at here is we are looking at certain key point like zero amplitude. I will narrow down on particle at zero amplitude. Because the moment I know this guy is at zero amplitude, this guy is at zero amplitude, I will know that at zero amplitude, he will be maximum pressure. Okay, zero, it will be maximum pressure. So I will know that it can be positive maximum or negative maximum. So how do I decide where is positive or negative? I will look at the picture as a whole, see whether is this a compression or is this a rarefaction. If it is a compression, I will know that this particular point will be positive pressure. If it's rarefaction, I will know that this particular point will be negative maximum pressure. Okay, so this is how I get the two important points. I look at the particle with zero amplitude. The next step I look at is actually I look at the particles with maximum amplitude. Because the particle with maximum amplitude actually will give me zero pressure. So on the picture, on the wave front, on the wave diagram, I will identify the next particle with maximum amplitude, which is the first particle here. Okay, so which means I know that the first particle, because he is at maximum displacement, okay, maximum displacement, I will know that the pressure at this location will be zero. Similarly, if you look at the picture here, you will find that this particular particle, original location is here. Now he is being displaced to the left, and left happen to be the maximum displacement. Okay, and this happened to be part of the what I call the second half of the wave itself. So when I know he's at maximum displacement, maximum amplitude, okay, I will know that the pressure will be zero. Okay, so this is how I decide, how I get the Q of these four important points. Because with these four important points, I will actually be able to draw the graph. I will be able to know that the graph will be of this sine curve shape here. Okay, whereby how to check your answer, you have to double check to make sure the conditions actually follows. Okay, so compression or refraction, it depends on the shape itself. So you look at the shape itself as a whole. Then how do I know is max pressure or zero pressure? Same thing, I look at displacement. Zero displacement, maximum pressure. Zero displacement, maximum pressure. Okay, similarly, maximum displacement, zero pressure. Okay, so these are the few points that I look out for, like maximum displacement, zero pressure. So for pressure distance graph, you'll find that I don't really need to plot every point. I will just look for the main key points, which is the point with maximum displacement and the point with zero displacement. And from there, I will be able to judge out or draft out the basic shape of the pressure displacement graph. Okay, and what with this graph, what can I look at? Okay, what information can I sieve out with? Okay, in general, the common things like, let's say for example, displacement distance and pressure distance, I can actually sieve out the cycle, the wavelength of the picture, the wavelength of the graph. Okay, because it's in distance, so I will be able to get out the what I call the wavelength, and with the wavelength, similarly to other wave questions, I will be able to use a formula v equal f lambda. We need to calculate the formula, the speed of this sound wave at this at certain instance. Okay, so this is one of the common questions that I get from students, whereby they look at how do I derive displacement distance graph, how do I derive pressure distance graph from the particle himself. Okay, you literally have to plot certain things like point by point to get the rough shapes that we are looking at. Okay, the next question that I get more often is, how do I know whether the speed of the sound has changed? Okay, in general, when you talk about speed of sound, you have to understand one thing is that if the wave is in the same medium, if the medium remain the same, one of the most common thing that we look at is that the speed will remain the same. So this is one underlying condition that I look at. So if I say that the waves is in air, if regardless of scenario, let's say in wave one or wave two, all these things, they're being transmitted in the same medium. Automatically, I will know that this information will tell me that the speed of the sound will remain the same. Okay, so in this case, I will say that my V will remain the same. And because V remains the same, you'll find that if you use the formula V equal to F lambda, if my V will remain the same, you'll find that the possible changes I can look at is my frequency of the sound could change. I could use a high pitch or a low pitch. Okay, while I keep the lambda remain constant. Okay, so this is one of the clue that I look at, is whereby I look at the question itself, whether the questions did it explicitly say the medium remain the same, or is it the medium has changed. So for example, if I say that the medium has changed, let's say the medium change, let's say example from solid, I change to liquid. So if the question has actually sieved out this particular information, what does it tell you as a student is that you have to know that it's telling you that the speed of the sound actually changes. The speed of the sound actually changes. And this change is something that you're familiar. Okay, when I go from solid to liquid, the speed of sound actually decreases. And since your speed is equal to F lambda, if my speed has decreased, I am able to infer it could be because when the speed change, what happened is the speed change could be because of frequency I can change, or frequency remain the same, or lambda changes, etc., etc. So from there, you'll be able to decipher whether f or lambda has they changed or have not changed. Okay, so you don't need to worry about too many factors remaining constant or remaining the same. So when I say the speed has actually changed, okay, means the medium has changed. I'm telling you that the speed has changed. So it could be a case whereby maybe the same sound is being used. Okay, so the frequency could be the same pitch. So as a result, my lambda of the wave will actually decreases. Okay, to cause a reduce in the speed itself. Okay, so at different medium here, we are looking at different story, a different question. The information that's given to you. Okay, you have to study carefully to make use of the information, to make use of the clues that's given to you, to derive at useful conclusions. For example, same medium, it means the same speed. And with that conclusions, it will able to help to simplify the math involved. Okay, so if you know that the speed medium changes, the speed change, and maybe the sound is remain the same, you will know that the lambda of the wave, the wavelength of the wave has actually changed. Okay, so with this, I run through some of the two common questions that I usually get in class for sound. Okay, it is not comprehensive, but these are the questions that currently I have in mind. So if you have any other questions that you like me to run through in class or run through on the videos, okay, just drop me an email at the comments bar. Okay, other than that, okay, any questions, okay, just drop me a comment bar. If not, then just click on the subscribe button to get latest update for the videos that are uploaded. Okay, if not, okay, all the best.